Okay, let's get started. Thanks for attending our webinar about energy storage and mission critical off-grid solar systems. This is Mark McHenry with Morningstar. I'll be your moderator and I'll introduce today's speakers. This is a very special energy storage partner joint webinar between Morningstar and MK-Deka, one of the most prominent companies in the battery industry. And as a reminder, we are recording this broadcast and we'll email all registrants and attendees a copy of the recording tomorrow. Also, we've attached 4 items in the handout section of the GoToWebinar pane. We recommend that you download them now. First item you'll see in your handouts is a copy of this webinar slide deck. The other items are a battery products brochure, a Morningstar Deka implementation guide, and Deka's renewable energy charging parameters document. That's going to be referenced in the presentation. So with that said, let me go ahead to the next slide and introduce today's presenters. From MK Battery, we have Dan Seidel and Doug Laningham. And from Morningstar, we have Jake Sherry. As you listen to the presentation, please text any questions you have in the chat section of your GoToWebinar console, and we'll address them at the end as time permits. Looks like Jake, you're up first, so please go ahead and take yourself off mute and take presenter controls and start the presentation for us.
All right, thanks Mark, appreciate the intro. So just to give everyone a little bit of background about Morningstar, for those of you unfamiliar with the company, we are a leading manufacturer of solar charge controllers and inverters. We have sold over 4 million of such products since our inception back in 1993. Those products have been distributed to over 100 countries worldwide for mission critical applications is really what we specialize in. Hence, it's a great marriage of the two companies here today, Morningstar and MK Battery, to highlight some of those attributes for mission critical applications. We do cater to residential and rural electrification, as well as commercial and industrial applications, really being the bread and butter of telecom, oil and gas, and security. And then, of course, we have been used in some recreational applications, including mobile, marine, and agriculture, in addition to others. We do consider ourselves as the charging experts. You can see that evidenced in the breadth of our product portfolio. We have by far many more individual product families, different sizes and capacities of charge controllers, all throughout the range, much wider and more diversified than any of our competitors. And we do pride ourselves in having the lowest hardware failure rate in the industry as well, something that speaks highly to our priority for reliability over everything else. So just to give you a little bit of conceptual background on how our main component, the charge controller, fits into the system. It is often considered the heart and brains of a solar electric system, mainly because it sits right in the middle of the solar panels and the batteries. And as the sun strikes the solar panels, you have the photovoltaic, photoelectric effect. You have the photons creating electricity that generates current through the panel, and that flows into the charge controller, and the charge controller then regulates that amperage and voltage to the battery without allowing it to become overcharged. So a lot of smarts have to be built into it to manage all sides of the system. In addition, you may find the inverters used in some of these applications that are converting the DC energy from the battery into AC power, and that would be used to power, critical loads that you might find in a household, some lights, computers, fans, etc. Would be found there. Morningstar only currently has one inverter that's shown here. That's our little SureSign 12-volt unit, but we are looking to expand that range as well. So stay tuned for more products to come. Again, the decision of choosing the right controller is not something you want to take lightly, because you see that reflected in an extended battery life. If you treat the battery as the manufacturer, who knows it best, says it likes to be treated, you're going to see that payback over a longer lifespan of the battery, whereas the wrong controller will quickly be evident in a shorter lifespan. In addition to the AC load examples you saw on the previous slide, many times the charge controller takes on even more functionality in terms of the load regulation. Now, many of the industrial applications still have loads that run off of just pure DC energy from the battery, but you need to make sure that you have some low voltage protection from over discharge of that battery. So many of Morningstar's charge controllers include integrated load circuits that can measure the current flowing to the load, as well as provide what's called low voltage disconnect, or LVD, to prevent discharging below a voltage specified voltage set point, and that's going to again promote much healthier and long life for the battery. Some of the DC loads, you'll see there's a lot of lighting, LEDs, DC LEDs these days. A lot of the consumer electronics take DC power, and again, in the more industrial applications like telecom, security, traffic control, you'll see a lot of pure DC loads. So again, the charge controller may take on even more responsibility in those systems. So the Morningstar is really the leader in two different types of solar charge controllers, those being MPPT, which stands for maximum power point tracking, and also the pulse width modulation, or PWM controllers. We offer a broad portfolio of controllers in both types, and regardless of the technology used, the primary objective of those controllers is to ensure longer battery life. Make sure you're harvesting as much power into the battery for reserves, for autonomy and run through, and then capturing that solar energy as efficiently as possible. You'll find that in both PWM and MPPT controllers alike. This slide just gives you an example of some of the core features and technologies that Morningstar is best known for. This is an illustration of our ProStar MPPT controller, which represents really the latest sort of amalgamation of Morningstar's core competencies and everything it's learned throughout its 27 years, crammed into a single product. It really has a lot to stand on. This controller features a built-in, optional built-in meter display that is fully programmable with a backlit LCD. It's very intuitive menu navigation. You can customize all types of settings straight from the meter display, and you don't have to lug your laptop out to the field and hook it in with a communication adapter. This makes it a lot easier. Also, you'll find characteristics like the high-speed ARM processor we use is really an impressive product that enables a whole bunch of functionality. The ARM processors are often used by a lot of high-end consumer electronics like Apple's iPhone or many of the like. And so again, you can imagine there are a lot of additional features that can be enabled down the road as the industry and the product matures. And again, we also use a high frequency design, which is, again, we purposely overspec our components, and that really improves the responsiveness, the control response, and it also guards against any sudden system transients, unforeseen, any type of regulation overshoot, overcurrent and overload conditions, we can respond and react that much faster. So those are really some of the identifying characteristics of Morningstar products. So the purpose of today's presentation is really geared toward our energy storage partner program. It's really a partnership between battery companies, premium battery companies, and Morningstar. Today we are showcasing MK Battery, which is, as Mark mentioned, a leading battery manufacturer in lead acid. They're also a neighbor of ours to the north, just in central Pennsylvania. And we've been working with them for many years to serve many of the same customers in some industrial applications and mission critical applications as well. The purpose of the program is to work with these battery manufacturers and iron out all of the compatibility and interoperability issues between our components so that the end user doesn't have to worry, and system designers can have peace of mind that all of that has been worked out. Our primary aim is really to make the installation a lot more plug and play, so that the settings are easily downloadable. You can, again, more or less set it and forget it. And again, this provides the ultimate end user of the product with peace of mind that their system has been proven, vetted by both parties, and it's well documented and supported by both parties in this case as well. So I guess with that said, I will transition over to Dan. I'm going to pass over the controls to your computer, but Doug is actually going to take over the slides. So just bear with me 1 second. All right, you should have the request there.
Okay, thank you, Jake. Appreciate that. Welcome, everyone, and thank you for joining us today. My name is Doug Lanningham. I am with MK Battery, as Jake mentioned. My colleague Dan Seidel, who will be speaking soon here, is our East Penn engineering support for the MK team. And then you can go ahead and advance to the next slide if you would. This is just a kind of an overview and structure of our company. East Penn is our parent. They are located in Lion Station, Pennsylvania. They own and operate MK Battery, who I work for. And MK is based out of Anaheim, California. eColt is our ultra battery technology. It's a newer technology. And this is out of Sydney, Australia. East Penn, Canada is based in Ontario. And then our international operation is in China. At East Penn, we are the largest single-site, privately held battery company. And we do have two manufacturing sites. Our main location, as I mentioned, is Lion Station. You can see the campus on the right there. It's over 600 acres. And we have a second facility in Corydon, Iowa. And as we grow and expand, we've had the need to expand into that additional operation there in Iowa. We were incorporated in 1947. And about 85 locations between Canada and the United States, with a global presence as well as distribution centers around the country. At East Penn, we're really proud of the fact that we have this vertical integration. It really does enable us to control our quality, our production standards, and cost. It's a very key component of our company. We have capabilities in a lot of these areas: plastic refinery. We have a facility, a smelter that does fully recycling our batteries on site. Carpentry, the tech center where we do a lot of our R&D and tear down analysis of batteries. Just a point of mention, from the time a battery is start to finish, through the line, it goes through a series of quality control checks, up to about 250 of those. So there's a lot of detail that goes into manufacturing of a battery. As I mentioned, we do have a full recycling and smelter operation at East Penn. We recycle over 30,000 batteries a day at that site, and annually that comes out to 200 million pounds of lead and 11 million pounds of plastic. So we're putting a lot through those smelters. We were the first to recycle battery acid, and we do hold a patent on that acid reclamation process. This next slide is our North American operation, our East Penn network. As I mentioned, we do have the warehouses around the country, but we do have distribution and stocking facilities, 51 of them in the United States. We have another 18 in Canada, with 2 manufacturing facilities, as I mentioned earlier, in Lion Station and Cordon. And then we have a warehouse in Mexico as well. We are, just another point of, sorry, Dan, the top right there in the yellow, you can see we do over 16.8 million units annually. That's units out the door to the customer site, so we are moving a lot of volume from these locations. As I mentioned, I do work for the MK Battery side, and our group is the energy storage team, which is a renewable energy team. Dan is part of that team. We have colleagues, Bruce Abeck, who does global sales for us, a gentleman that covers Latin America, Charlie Stanford, and good engineering tech support out of our Anaheim office, that's Grassi Rosen. So we're a small team in number, but we do focus on this industry as so renewable. As far as locations of MK, we have 20 U.S. distribution centers, which are those warehouses represented in the map. We do stock and inventory batteries at those sites, as well as pick up spents and recycle, pickup service as well. We have 4 sites in the UK and a site that covers the Netherlands, Germany, and Australia. This next slide is our battery offering, and these really are the core batteries that go into the renewable energy industry. All are manufactured at East Penn. A point of mention is there's a lot of labels on batteries out there. MK will put labels on batteries. The Deka solar label, which you see in the pictures there, is kind of the trademark label for the renewable industry. So I just wanted to point that out. If you see those labels, you know it's coming from our team. We have both monoblock and 2-volt product. The monoblock comes in 6-volt and 12-volt. Battery flooded wet cell types, AGM, which is absorbed glass mat, as well as gel cell technology. Same thing in the 2-volt. We offer the 3 chemistries. And again, we have different offerings that really enable us to kind of point the customer into the right direction with the right choice. So we'll talk about that on the next slide here in a little bit. By the way, this chart is located that you see here for applications on our complete line brochure, which should be included in your packets today. And it's a very good informational reference when choosing a battery for your design. We ask that you take a look at this just as an initial starting point. If you're cycling the batteries routinely, you can kind of go through there and quickly identify if a battery meets your cycling needs, as well as temperature type considerations, maintenance, and other things like installation, orientation. So good reference, but always feel free to pick up the phone. We're happy to help anytime. This final slide before I pass it over to my colleague is our renewable energy charging parameters. We always like to state, very important to go with the manufacturer set points. And there's no exception with us. We do publish these settings for solar-based locations. We do offer the voltage settings in a 2-volt, 24, and 48-volt configuration, so you can quickly program those for absorption, float, and equalize. And again, you can find this as well on our MK Battery website, and it's at mkbattery.com. And at this point, I think I'll pass it over to Dan Seidel again, who is going to really get into the meat of the presentation today, talking about proper charging as you're setting up your controllers. And Dan, it's all yours.
All right, thank you, Doug. First thing I want to make sure everyone's understanding the following topics of discussion are centered around off-grid systems. And one of the most important parts of a properly functioning energy storage system is the setup of the battery charging system itself. The preceding topics attempt to highlight this along with the ramifications of improper charging. So what we're looking at discussing today is highlighting the importance of the charge voltage settings, the battery charge current, the discussing about absorption time setting, and then touching on valve regulated lead acid batteries and the ability to equalize those batteries. So the first thing I wanted to talk about is charge voltage differential. Going back a couple slides here, you can see that we give a range of, for absorption stage, we give a range of 2.35 volts per cell, to 2.4 volts per cell. And that is because a lot of equipment, either that you're connecting to on your charge controllers or your inverters or even some other equipment, may not be able to handle the maximum charge voltage that we recommend. So we do give a range. But what I want to discuss is the impact of that range and the reason why it should be at the highest setting as possible. Now, in this slide here, you'll see I have a voltage range of 2.30 volts per cell all the way up to 2.40 volts per cell. For our 8G and 8A product, our monoblock valve regulated, this goes into multiple different types of equipment. And other applications, we have the voltage range of 2.30 to 2.4. For solar applications, we recommend no lower than 2.35 and no higher than 2.40 volts. So what we had done, we were looking at to see what's the real impact at these different voltage levels. So we ran a test and we discharged the batteries at 100% depth of discharge. Now, that which is untypical of a solar application. Typically, we don't go below between 50 and maybe 70% depth of discharge. So the numbers I'll show you on charge time are a little bit higher than what they normally would be in a system, but the impact of the voltage variations will be the same. The other way to look at this is if your charge controller, you set the charge controller at 2.40 volts per cell, and you have a voltage drop between the cables and because of the distance from the charge controller to the batteries, you have a voltage drop of 0.02 volts per cell. So now the battery's feeling a 2.38 volts per cell charge. And just to clarify that, we use a typical three-stage charging, your bulk charge stage, and we use the absorption stage. Now, staying with the voltage drop, you can see here that 28.8 is the 2.4 volts per cell charge. And to get 110% back into the battery of all the amp hours that we removed, it took 35.1 hours. Now, if you have that 0.02 voltage drop across the cables, or the distance between the two, and the battery seeing this 28.56 or the 2.38 volts per cell, you will see that it will take 63.8 hours. Now that's a 1.8 or almost 2 times the time it takes to recharge the battery at 2.4. So that can be a fairly big impact on the entire system. The advantage of having a higher voltage is the battery will stay in this bulk stage, bulk start charging stage longer. And what that means is you will have more of your current going to the batteries. If you have 25 amps, you'll have 25 amps going to that battery steadily until it reaches that voltage, where it would kick down, where it would change from a bulk to absorption when it hits that limit. So the higher voltage you have, the longer it takes to get to that voltage before it starts to taper. Essentially means the more amp hours you're going to get back in the battery. And here you can see at the 28.5, you get 84% back in within that time period of the bulk stage. Or at 28.8 for the 2.4, you're getting 86% back in. Now, if you go all the way down to our lower limit of 2.35, you're only getting 80% back in. Now, it doesn't seem like a lot of 4%, 6% difference between those, but think of it this way: is every day you're possibly getting 6% less amp hours back in the battery, and essentially that's 6% less capacity. So it's really important because with the solar system, as you all know, the sun regulates what the power we're getting back in an off-grid system. And the sun is not very reliable. Again, today here we had bright sun during this morning. I had an hour and a half there of cloudy day of showers, and now it's sunny again. So it's very unpredictable. So the more you can get back in to that battery, the better. So our recommendation is to use the high voltage, high setting. And like I said, if your battery, if you have a significant voltage drop, then the charge controller should be set higher to compensate for that difference. So you're up more around this 28.8 or the 2.4 volts per cell. Staying with that, the other important aspect of setting up the battery charge controller or the inverter correctly is the amount of current, charge current that's available to the batteries. So we had looked at this and we developed we call it a charge current verification. And for using this to identify the necessary charge current required for the system. So this would be calculations you would do during your design phase of the battery, of the whole system. You know, what kind of charge controller do I need? How much PV do I need? And the impacts of the two. So the two equations are the bulk stage time calculation and the absorption stage time calculation. The parameters for both of those I will go over in the next several slides. And the total time of the bulk and absorption stages must be less than the average daily sun hours for that installation location. So this calculation really isn't a one calculation fits all areas. You'd have to make sure that for the area you're installing this, whether it be Alaska, whether it be Texas, whether it be Pennsylvania, that you're within these parameters. And if the combined time is greater than the average daily sun hours, charge current to the batteries must increase, or the batteries will be undercharged, resulting in decreased battery life. So these calculations is more of an upfront to say, okay, do I have enough going to the batteries or don't I? And if I don't, for this particular area, I have to reevaluate, should recommend reevaluating your system till you get to the point where your average sun hours are equal to or less than, this calculation is equal to or less than the average daily sun hours for that area. And going into the details, the bulk stage time calculation, it's the amp hours you remove from the battery times a recharge efficiency multiplier of 1.2, because as you recharge the batteries, there is some efficiency losses. The efficiency loss is due to when you recharge the battery, you're converting the electrical energy coming in back to chemical energy. And that takes time, and it takes some of that efficiencies out of there. So you want to compensate for those differences. And then you divide that by the charge current. And the charge current I want to highlight on this, the charge current is what is available to the batteries after the load is satisfied. So if you have a 100 amp load and say you have a 100 amp charger, charge controller and inverter that's capable of 100 amps, but you have loads on the house or loads wherever that would take 50% of that. So the solar panels are supplying power to those loads, plus they're supplying power to the batteries. So it's important that the value you put in there is the estimated current that will be available to the batteries after the loads are satisfied. Because if you use what's coming out of the inverter or charge controller, it's going to skew the calculations and it won't be correct. And then the result of that is the bulk time, the calculated charge time at bulk stage. On the absorption side, we do the same thing, use the amp hours removed times this 1.2. The difference is because in the absorption stage, the current is always decreasing, because as it hits that voltage limit, the current starts to decrease in that phase. We looked at this on average, and we took an average current during the absorption stage. So that's what these factors are. For our flooded type batteries, that factor multiplier is 0.44. And for our regulated batteries, that factor is 0.39. And again, the charge current that you plug into this calculation is what's available to the batteries after the load is satisfied. And that then becomes the absorption time, the calculated charge time of the absorption stage. So on the next two slides, I'm going to go through some demonstrations on how the amount of current impacts the overall time, over the overall calculated time to recharge that battery. So in this example one, I picked a installation location that had average winter peak sun hours of 3.9 hours. And we used our battery type, our 8G4D, which has a C20 capacity rate of 183 amp hours. And with all of our batteries, all of our gel batteries, it's a 30%, the maximum charge current is 30% of the C20. And our other batteries may have different limits for that. The renewable energy charge spreadsheet that Doug had spoken earlier that's in the attachments verifies and clarifies what batteries have what limits. So for this calculation, this exercise, we use the maximum charge current, which 30% of that C20 of 183, it's 55 amps. So if we go through these calculations, what we did is I looked at taking 50% out of the battery. Again, because that's typically how much capacity is taken out of a battery when it's discharged in a off-grid system. So 50% of the 183 is 91.5 amp hours times the multiplier, the efficiency multiplier, divided by the 55 amps, and that comes out to 2 hours of calculated time it would take that the battery would be in bulk stage. On the absorption stage calculation, we use the same 50% depth of discharge, the multipliers. We multiply that times the 0.39 multiplier for regulated batteries, divide that by 55 amps. And that is essentially, that calculation comes out to about 0.78 hours or close to 3 hours. So our total calculated charge time is 2.78 hours, and that is adding the bulk and the absorption stage. For this demonstration, that calculated time is less than the peak sun hours of the site location. So there's a good possibility that you will get these batteries fully charged. Now, taking that to the other extreme, to the lower end, if we use the minimum charge current allowed that we recommend that to be 10% of the C20. So for this particular battery type, that's 18.3 amps. And again, we're using the same battery type and the same installation location. And if we go through them same calculations again for the bulk stage, going down to 18.3 amps, it increases the calculated bulk time to 6 hours. At the same time, we do the absorption stage time calculation, and again, we use the 18.3 instead of the 55 amps, and that increases our calculated absorption time to 2.34 hours. So our total calculated charge time is 8.34 hours if you add up the bulk and the absorption stage. Now, if you remember in our example here, we say the average winter peak sun hours is 3.9 hours. So this calculation is less than the calculation is greater than the peak sun hours for this site. So going off the chart here to the right, you can see graphically how the impact of that is. Again, our average sun hours was 3.9 hours. We calculated using our maximum charge current, and we would get 2.78 hours. And if we would use the minimum, you can see the impact of that is 8.34 hours. So if you look, I have it broken out here in the example 2. We have a bulk stage that takes 6 hours, calculated at 6 hours. Now, you can see that we only have 3.9 average peak sun hours at this location. So this battery, using the minimum, would never get out of the bulk stage. And this battery would be consistently undercharged, which would result in decreased capacity over time and premature battery failure. So, Jake, I'll send it to you.
Sure. Just wanted to interject and provide a little bit of the relation back to the charge controller, piggybacking on Dan's example. If you, again, take the same system parameters that we were discussing before, you can use this information to validate your charge controller selection. So just to demonstrate that, again, for this particular system, you had a 183 amp hour 8G 4D battery, and we've calculated the maximum charge current based on the 30% of the C20 at 55 amps, and then the minimum charge current is the 10% of the C20 rating, which would be 18.3 amps. So if you go ahead and looking through Morningstar's product portfolio, you choose a controller with a rating somewhere in between those two thresholds, then you can take it through the bulk and absorption time calculations to sort of check and make sure that it makes sense. Now, we've chosen the ProStar MPPT 40 in this example. Now, that's 40 amps of charging, but as Dan mentioned, if you have loads that are active during the day when sun is available, a certain portion of that current coming from the solar array is going to your load and not to the battery. So you do want to make sure that you compensate or accommodate for that in your calculations, that it is the current going to the battery and that you, again, you have to take the load out of the total current coming in. But for the purposes of this example, just assume, the loads are only active at night when the solar is not charging. So again, if we use the 40 amp rating of the ProStar MPPT 40, we go through those bulk stage calculations. Again, the 91.5 amp hours times 1.2 divided by 40, we end up with a 2.75 hour long bulk stage. And then if you do the same thing with the added step of multiplying by the 0.39 compensation factor for the absorption time for VRLA, we find that it's 1.07 hours of absorption. Adding the two together, we see the total charge time to get through both of those stages is 3.82 hours, which again is just underneath our 3.9 average peak sun hours over the winter months for this site location. So you can see that in this ideal scenario, this charge controller would check out. So that's just kind of a good way to, check your math and make sure that, you get, you can validate your charge controller selection, that it's the right match for this battery and this particular site. Back to you, Dan.
All right, thank you. With that, now those calculations that we just went through, that's in a perfect world. That's, but as we all know, in off-grid applications, there is no perfect world. We're at the mercy of the sun. So there's some days you may get more sun than other days. So we would like to discuss the ramifications of that on the absorption charge, the absorption setting. For time-regulated absorption, we recommend setting the time to the maximum possible setting that charge controller or the inverter will allow. And our recommendation is a minimum 8 hours. And the reason for that is, on average, around the country, the highest full exposure, full sun hour days is 6.6 to 7 hours. So we don't want to go below that. We want to take advantage of all that available sun throughout the day, not just for what we estimated that charge to be. And what that does is, then there's no seasonal variations. The sun availability determines the absorption time. And as we all know, during the summer in the United States here, we get more sun available than we do in the wintertime. There's an impact between the two, a very wide variation. So to demonstrate that, what I've done is I just came up with a hypothetical system install. So the PV panel output, the calculated PV output is 600 watts. And if we say we have a house load of 300 watts, so that means there's charge availability or power to the batteries at 300 watts. And if we use our calculated recharge time that we looked at before in our demonstrations, our examples, we use 2.78, or say it takes 3 hours. So here on the right, I took the orange would be the calculated charge time. The green is the remaining available charge time, and the black would be the house loads. So we see here through the whole day, this 300 watts is taken up. So we will concentrate up here on this area. You can see throughout this day, we have a full 8 hours of available peak full sun hours. But we theoretically only need 2.78 or 3 hours of that, which is the orange. So we have all of this remaining here. Now again, this is that calculated absorption and bulk stage charging is in a perfect world. And as we said, we have no perfect world. Well, 2 days ago, you would have had, say we had partial sun. So we didn't get as much recharging of the batteries that day, but we still had that same demand overnight. So now your battery is a little bit more discharged than you normally would. The next day, you have a little bit more sun, but you still have a little bit of clouds. So now that battery is being discharged a little bit less. Now the third day, you have full sun. You can replace all the power, all the amp hours you used overnight. But what about the last 2 days where you didn't get to recharge, didn't get to put all the amp hours back in to recharge that battery fully each day of those 3 days? So our recommendation is, by opening this up to the full absorption stage for them 8 hours, you're taking advantage of getting as much amp hours back in this battery to make up for those differences for the 1, 2, 3, 4 days prior to that. So by just using your 3 hours, you're cutting yourself short on that, which could lead to undercharging of the battery, which would be charge deficit, which would you lose capacity, which would you lose your battery life. Excuse me. Now, on the other side of that point, in the wintertime, as you know, we have less available sun. So again, using the same parameters as 600 watts, 300 watts for the load, and 300 watts for the battery, and the 2.78 or essentially 3 hours. You can see here we have, there's a huge difference in how much available sun we have. We need 3 hours, calculated 3 hours of that for this bulk and absorption. So for the peak full sun, we only have an hour left. But we had set the absorption time for 8 hours. So what that does, it actually gives us the time. So now we have all of this area in here that we still have not peak sun, but we still have some sun, and we still have some power that's available to the batteries. So this would, by keeping that open, we would put all this extra amp hours back into the battery. Again, because in wintertime, it's even more essential to get as much as you can back in, because as demonstrated here, there is a lower or a short window of how much peak sun we have. So the more we can get into the battery, the better off over time you are, the more amp hours you'll get in, and the less chances you have of undercharging the battery and shortening the life of the battery and reducing your capacity. So on the equalization portion of this, it's always been said that valve-regulated batteries should not be equalized on a daily basis. I'm sorry, they say it shouldn't be equalized. We say that that holds true for daily exercise of recharging and equalizing daily. Now, for flooded batteries, it always is the bulk stage, the absorption stage, and then you do a constant current stage at the end. We do not recommend doing that on a regular basis for these valve regulators. We recommend doing this as an alternative to bringing the battery to a full state of charge during periods of limited sun. So if during your bulk stage here, you still didn't get enough back in that week, in that time of 2 weeks, we recommend that you do an equalized charge. Either, it all depends on your area, if you would do that on a monthly basis or do that every 2 weeks. And if we do publish limited voltage. We recommend 2.43 volts per cell on our 8A and 8G batteries as the 8G4D that we used in this demonstration, and that will not affect the battery life of the battery. We did multiple testing to show where the gassing of that battery, where that upper limit is. And for equalization, if you do that on a 2-week basis or a monthly basis, you will lose some gassing, but not a lot. We did this over a 3-year period where we discharged the battery, and we did equalized charge every 15 days or every 2 weeks. And we had minimal gassing over the life of those 3 years. So again, that's as long as it stays within our limits. And the alternative of not equalizing is the battery will fall into capacity deficit and cause irreversible sulfation. The sulfation is when you discharge the battery, the added material that takes the chemical and converts that to electrical current to charge and for your loads. Then sulfates, if you don't convert them back over during your recharge, those sulfates will become hardened like hard crystals, and then it's very difficult to convert those back. So essentially, you're losing capacity. So if you do these equalizing, on a quarterly, every 2 weeks or every month, it helps to bring as much current back into that battery as you can, and amp hours to recharge the battery. And again, to emphasize this, that equalization would be for off-grid applications only. For grid-tied applications, that battery is essentially in a float stage. It's essentially sitting there charging all the time. So it's not necessary to do an equalization on a system like that. And even when you do use the battery, when your utility power comes back, you have a reliable source of power to recharge those batteries. So you would need to do an equalization on those types of systems. So in conclusion with this, on the charge controller and the inverter battery charge settings, the default settings should not be assumed to be correct. We recommend using the battery manufacturer charge settings recommendations. And on the voltage setting, we recommend using the maximum voltage settings allowable by the charge controller or the limitations on your equipment that may be connected to that. And again, and also with the current setting, again, use the maximum recommendation. And again, as we went through those calculations, by using anything less than that impacts the amount of time it takes to recharge that battery. And in these types of systems, especially the off-grid system, we're at the mercy of the sun. And unfortunately, as we all know, it's very unreliable. So the more we can get into that battery on both the charge settings and the current, the more amp hours we get back in, the better off we are in the long run, the better off the battery will last longer and meet or exceed the expectations that you have put on that battery. On the absorption time side, we recommend to set it to the maximum time that allowable by the charge controller or the inverter, regardless of what the calculated charge time was on the exercises we went through. Again, that is to get as much power back in the batteries as possible, and we don't want to limit what we can put back in there, because in the long run, again, shortens the life of the battery and you lose your expected capacity. On the equalization, this is permitted for valve-regulated batteries and off-grid systems to recover the battery during periods of limited sun. So again, that's either on every 15 days or 2 weeks or every 30 days, depending on your location. And unfortunately, that may have to vary wherever you're at, because in the wintertime, you may need that every 2 weeks versus in the summertime, you may only need that once a month, or you may not need it at all. So with that, I will send it back over to Mark or Jake.
Sure. Great. Thanks. Thanks, Dan. This is Mark. Thanks for the presentation. We do have a number of questions that came in. So let me start off. First, I have a question for Jake. Question is, how do you change the charge settings from the default settings on the ProStar MPPT controller?
Okay, so that's a good question and very relevant to our discussion here today. So on the ProStar MPPT, there are 8 dip switches that can be used to configure various presets that are stored in the controller straight from the factory. So if one of those presets happens to line up with the battery you're using, again, most of the presets are formulated for lead acid, but as Dan mentioned, it's important to get the guidance and the precise settings straight from the battery manufacturer. So you want to get ideally as close a match to that as possible. What we've done with MK Battery is we've actually, again, through our energy storage partner program, we've gone ahead and documented all of the settings requirements as discussed here today and configured them into our MSView setup files for easy upload to the controller. So if you are interested in using an MK or Deka battery, then you can find those custom settings, taking into consideration all of the parameters we discussed today. They've already been filled out in uploadable configuration files using our MSView software. You will find that information in a document. The implementation guide, as Mark mentioned early on, is in the handouts section of your GoToWebinar pane. So within that document, it's a PDF. There is a link to download the MSView configuration files that are stored in a zip folder on our web server. So all you do is just export that zip folder to your desktop, unpackage the contents, and read the appropriate file for your controller with our MSView software, and then you can program it, making it very plug and play. That was sort of the aim of the integration here today. So hopefully that answers your question. If you do have any issues accessing that documentation, please let us know.
Okay, great. So thanks for that answer. And Jake, I see another question here for you. Question is coming in from Fernando. The question is, I see the ProStar has a built-in surge suppressor. Does the TriStar MPPT 60 also have that feature?
So just an important distinction to make here with the surge suppression. This is not like any degree of protection against lightning or really high voltage or high potential surges. This would be more for board level protection in terms of what's built in standard to our controllers. So all of our controllers have transient voltage suppressors, or TVS transorbs, which are just solid state components on the board that basically protect it from getting fried by those transients. But it's really meant for more minute transients. If you're talking about lightning, if you're in the vicinity of nearby lightning strikes, then you're going to want beefed up enhanced surge protection. You're going to need a proper surge arrestor or an MOV externally that you would add on to your system. That MOV is metal oxide varistor. Those are not quite as quick to respond as the transient voltage suppressors, but they can tolerate larger spikes. So again, if you're talking about lightning protection, that does not come standard. You would have to, again, if you're in really lightning prone areas, you're going to want to add that on externally.
Okay, great. Thanks for that question. Thanks for the answer. Here's a question for Dan. Actually, we had a couple people ask a similar question to this. It says, your slide showed Equalize for an HE battery. Do you actually recommend Equalize on a gel battery? Some people might have missed that a little bit. Do you want to go over that a little bit, Dan? Like how often and when you would need Equalize on a gel battery? And a lot of people were surprised. They didn't think that they should be equalizing that a gel.
When valve-regulated batteries first came out, they were in a high competition with flooded batteries because everyone had flooded batteries. So at the time, it was all the chargers were set up to have the bulk stage, a absorption stage, and then do this equalization stage at the end, which is typically a constant current, which is another bulk stage. They would increase the current on that. And with a flooded battery, you can replace that water on a daily basis, because when you charge the battery, it gets the full state of charge, that you get your gassing, which is your hydrogen and oxygen, which is essentially water. So when valve-regulated batteries first came out, because of this variation, there wasn't many chargers available. It was said that do not equalize the batteries. Over the years, we have done significant amount of testing, and we recommend that you can do equalizing, But the equalization that we recommend is still a voltage regulated charge. It's not a current regulated charge. It's a voltage regulated charge. And our voltage, our limit on our absorption stage for standard charging is 2.4 volts per cell. So for equalization, we recommend going to 2.43 volts per cell. That 2.43 is a higher voltage than the normal, but it's still under the threshold of the battery having excessive gassing. If you go over that 2.45, 2.5 volts per cell, you would have excessive gassing. And with a valve-regulated battery, there's no way to replace that hydrogen, oxygen, or essential water in that battery. You could dry out. So you can equalize these batteries, but again, we do not recommend doing that as a daily basis. We recommend that only if the battery needs some extra charge. Say you had a week or 2 weeks full of 1 week that you didn't have much sun, so you could do this equalize every 2 weeks to take up those differences. So it's more, I wouldn't call it an equalized charge. I would call it more of a maintenance charge. So to help maintain the battery and help maintain the battery at a full state of charge. So again, we do recommend that it can be done, but not on a daily basis, just on every 2 weeks or every 30 days, or when it feels that you had a long period of time that you didn't get sun and you felt that the batteries are being undercharged. On that renewable energy charging parameter spreadsheet, it goes over those parameters in there. We have the voltage limit, and then there's also the time limit on there. So as long as you stay within our recommended parameters, and again, do this every 2 weeks or every once a month, it will not affect the life of the battery. It won't shorten the life of the battery. By not equalizing, then by not doing an equalized charge when needed, you would shorten the life of the battery because you'd be undercharged. So hopefully that answers the question.
Yep, very good, very good. Okay, so that takes care of that. I see a question coming in from Theodore. He says, I currently have 4 8L16 Deka batteries. They are the ProMaster series. Is there any material significant difference between the Deka ProMaster line and the, let me see if it cuts off, and the solar line of batteries?
No, they are essentially, it's the same battery. It's just different labeling. But I can say that with, go ahead, Doug.
I apologize, Dan, for interrupting. Go ahead and finish, and then I'll jump in. Just a comment, Mark, and to the person who asked the question. The labels that I mentioned at the beginning of the presentation, that there are different labels that get put on batteries. A lot of times the labels will specify the application where we're going, and we have very specific charging parameters, as you've seen in our renewable sheet. So the labels will dictate proper charging, and again, I think in the case of the ProMaster and some of the others, it may be more specific to more of a starting application, as opposed to maybe in the case of what we're doing with solar, where we're typically cycling these routinely in an off-grid system. So just a comment there. Go ahead, Dan.
Yeah, and actually, and Doug, that was the direction I was going to go. An example of that is, as we mentioned earlier, the overall gel battery or then flooded batteries have a set variation. For example, for the gels, we say 2.30 to 2.4 volts per cell is the parameter range for multiple applications. But for renewable energy off-grid systems, we have a tighter recommendation of the 2.35 to 2.40. And as Doug mentioned, our labels are more to the label would say that on there. So if you would use the other type battery, you could get different charging parameters and possibility of undercharging the battery.
Okay, very good. I see a question here that reads, how does the higher charge voltage affect life of the battery? And this is for, I would say, for Dan or Doug.
The higher charge voltage, as we demonstrated, as long as you stay within the parameters we have done extensive testing, and our parameters that we publish will not damage the battery, overcharge the battery, excessive gas the battery. So our recommendation is to keep it at those higher settings within our parameters, and as you can see, the impact is you would get more charge back into the battery. The other side of that coin, if you use the lower end of that charging parameter, you can see where you would shorten, you wouldn't get as much charge back in, and you have the possibility of undercharging the battery.
Okay, thanks for that.
It's worth pointing out, Mark, also that the majority of the batteries that we bring back in for a teardown analysis that are off-grid standalone systems do come back as damage due to sulfation because they're sitting in a partial state of charge, as Dan is talking about in the presentation. So just want to make that note that the trade-off actually for the higher charge setting is a good trade-off, because that's typically what we do see when we do the analysis in the lab.
Okay, very good. Here's a question for Jake Sherry. The question is, charge controller current limit is the total current, in other words, the battery and load, but the load may vary. Do you have a charge controller that measures actual battery current?
Let's see, that's a good question, but let me just see if I understand it correctly. The charge controller current limit, so like the rating of the controller, say it's the ProStar MPPT 40, has, would that just be the charging current, or would that be both the charging and the load current combined can only be 40 amps? The answer to that would be those are independent ratings. So the 40 amp rating of the ProStar MPPT 40 is for the charging, and then there's also a 30 amp load rating. So those can be going simultaneously. If you had 70 amps, but 30 amps was going to the load, and again, not exceeding the 40 amp rating to the battery, that would still be acceptable. So the load and the charging circuits are rated independently, if that answers your question to some extent. But if you're talking about actually measuring battery state of charge, in that case, again, we don't have you would need like a battery shunt actually measuring the input current and the output current. We can get a net current measurement if you're using one of our controllers. And again, if it's just a standalone system with a single controller that also has the integrated load circuit for the DC loads, then you can get a net current measurement ideally. And if we had sort of the developed algorithm, we could potentially calculate the estimated battery state of charge. But the best way to do that is with an external shunt. And they make, many third-party battery monitors out there. I think one that I often refer to is Bogart Engineering. Their trimetric is sort of widely used, has been used in many cases with Morningstar products, just as, a more accurate indication of the battery state of charge. So if that's what you're looking for, that's, again, something that would be an external component, as we do not offer that.
All right, thanks for that question. Thanks for the answer. Next question, I'm going to break into a two-parter. So first part is, can you do an example at 20% discharge rather than 50%? That's the first part. And then, is there any comment you'd like to make on and you might have to take this offline, but any comments you'd like to share about using a 5-day battery per IEE, IEEE 1562? Is there anything you'd like to address regarding that recommendation? So I guess first we'll start off with the 20%.
Yeah, I mean,
discharge
the
example.
the example I had given was just, yeah, you can take that, and if you're taking 20% out of the battery, whatever your battery type is, you would multiply it by 20% and use that in that calculation rather than the 50% level that I had used in my example. Then that would go through the equation, and you would get your estimated time, your calculated times. So yes, you could. It's not hard set on that. Those are all variables that you could put in that battery, that you could put in that equation.
Gotcha. So I think that what you were just showing was just for really example purposes, and yeah, you could really use, depending on your system and the requirements, really just plug in different numbers.
Right. And the second part of the question, I think we'll have to defer that to later. I'm not quite sure what all that with the IEEE 1562. So we'll have to review that.
Okay, sure. Good enough. All right. Okay, here's a question from James. Let's see. He had a question about the absorption time calculation. He said, should the 0.39 factor be in the denominator? In other words, should it be 0.39 of the charge current rather than 0.39 of the amp hours? So is that a question you'd be able to answer for James? And this would be for Dan or Doug.
I'll have to look at that. I mean, that's the equation we came up with. So if I can defer that for later.
Sure. Okay, good question, and we'll get back to you on that. Let's see. Looks like I have there's a really long question in here. Okay, question here is, how do I know the state of charge is 50% by using voltage as a parameter? And this would be either for Jake, Dan, or Doug.
Okay. I guess, Dan, do you want to take that?
Yeah. I apologize. Can you repeat the question, please?
Yeah, sure. It says, how do I know the state of charge is 50% by using voltage as a parameter?
That's very difficult to do in a system that is on charge, because as you're charging the battery, once the battery reaches and you get the bulk stage where the current is constant, the voltage is increasing. Once it reaches that, you're at 90%, 85 to 90% state of charge. But then your current starts to taper and that voltage is holding on. The only way to use voltage as to determine the state of charge of the battery, to give an accurate state of charge, is to have the battery on open circuit or with no loads on it, no charge, no discharge on it for a period of 24 hours. And once the battery settles, then you take that open circuit reading, and then we have charts in our I&O manuals that'll say, okay, if it's above 2.8, it's at 100%. If it's 12.6 or something like that, it's at 75%. So the only way, our recommendation is on charge, the only way is to monitor the amp hours in and amp hours out of the battery. And again, that can be done, as Jake had said, with a external shunt that a battery monitoring system would be able to keep track of. And you would want to look at it as an overall state of charge. Not today you had 100% state of charge, you got everything back in, but tomorrow you didn't. there are some of these monitoring systems that it resets itself once it sees another discharge coming in. So once a discharge comes in, it counts down how many amp hours to take out. And then when it feels it's starting to charge, it counts up. But unfortunately, we found that some of those, when you get another discharge, it goes back to 0. So it's not keeping a track. You want to look at the overall state of charge of the battery. So again, just in conclusion to that, you cannot accurately determine the state of charge of the battery when it's being charged. The accurate way to do that is to using an amp hour counter, which requires a shunt.
Okay, good enough. Let's see, there's a number of questions that came in about accessing the presentation slide deck. So that's actually in your handout section of your GoToWebinar console. So if you look at your console and you see handouts, if you click on that, it's actually 4 attachments, and one of them, if you download, is the presentation. So you can get that. Also, we did record this, and we will send you a recording via email tomorrow of this presentation. Looks like just time for one more question. This one looks like it's for Jake. Question says, how do I differentiate between PWM and MPPT charge controllers?
All right, that's a good question. So we do have a white paper on our website that does compare the 2 different types. So that's a good resource to reference if you would like some more detail. But in general, the PWM controllers, their sort of limiting factor is that they can only operate the array at the voltage of the battery. So you have to always make sure that you can configure that array using nominal voltage panels. So if it's a 12-volt battery, you would use what is typically a 36-cell solar panel, which has the operating max power point voltage at around 17 to 18 volts. That's ideally suited for PWM controllers. With MPPTs, you can actually, it's got what's called a buck converter, so it can actually step down from a higher voltage to a lower voltage and boost the current on the output in the process. And those types of controllers, again, then can tolerate less common voltage configurations that are much higher in terms of the array output. So you can, wire a higher voltage array, which has some benefits in terms of mitigating the effects of voltage drop over a longer wiring distance. So in those cases, an MPPT controller can be useful. And in particular, you're going to find the most benefit of an MPPT in colder temperature climates. Those cold temperatures have an effect on the module characteristics, the solar panel, that has, an associated temperature coefficient where the voltage will rise with each drop in temperature. Each degree Celsius or whatever it is will end up elevating the voltage of the array. And in that case, you really want to have an MPPT controller so that you can efficiently convert that voltage differential into a current boost, harvesting as much energy in your battery as possible. That's sort of the main difference between the 2 types. But again, I urge you to check out that white paper on our website if you get a chance.
Okay, terrific. If you want to advance the slides to the thank you slide, we have gone quite a bit past the hour. There are a few more questions actually in here that we weren't able to get to. Some of them are a little bit long, so it's probably better we take them offline. They look pretty specific, so we'll have to probably take them offline anyway. But really appreciate everyone's time here, all the presenters from MK and Morningstar, as well as everybody who attended today. So terrific. We'll see you next time. With that, we're going to just leave up this thank you slide for a little bit. So if you need to contact us, you see MK's contact info at the top of their website. mkbattery.com, the phone number. Also underneath that, you see the morningstarcorp.com website and contact information there. So again, thanks for attending, everybody. We'll conclude the broadcast. We'll see you next time. Thanks so much.
Thanks, everyone.